My name is Sharath Israni. I work in the Dean's office in Stanford Medicine, and we have a data science in Stanford seminar series that we do once a month during the academic year, where we get some really distinguished speakers, such as the one today, to come and tell us applications of data science and sometimes the foundations of data science, as they see it. It's a very complex subject, no question about that, and a very exciting one. There are a couple of names that you see emails from and who actually are a major part of setting up this series. We've had only very successful talks, just as I can see this one shaping up as. I want to acknowledge those people over here. And one of them is Brooke Zelnick, who, right there. Another one is Janet Kalesnikov, the one right in front who you can see. And these are people that are behind the scenes that help us. We also work in association with, and he's not here today that I can see, Steve Eglash, who is the executive director for Stanford Data Sciences Initiative. All of this is encapsulated in a website called datascience.stanford.edu. That URL alone is worth $1,000 if anyone wants to bid for it. It is my extreme pleasure to introduce today's speaker. Let me tell you a little bit about him. David Lobell is an associate professor in Earth System Science, deputy director of the Center on Food Security and the Environment, and a William Wrigley Senior Fellow at the Stanford Woods Institute for the Environment and the Freeman Spogli Institute for International Studies. His research focuses on identifying opportunities to raise crop yields in major agricultural regions, with a particular emphasis on adaptation to climate change, which I could tell you is one of the White House priorities. Climate change is a major White House priority, including for data science, and they have come out and said that. His current projects span Africa, South Asia, Mexico, and the United States, and they involve a range of tools, including remote sensing, geographical information systems, I think that's what GIS is, and crop and climate models. It's no surprise that when you research questions, such critical questions of national and indeed global importance, that David is a hugely sought after speaker. I can tell you from personal experience that when he spoke at the Parents' Day at Stanford, it was hard to get inside the memorial auditorium, and I'm sure there'll be more of those coming as a result. David received a PhD in geological and environmental sciences from Stanford, and an SCB in applied mathematics, magna cum laude from Brown. And in case he doesn't say so himself, David was a MacArthur Award winner in 2013. Please welcome David to talk about the subject.
Okay, well, thank you, Sharath. All right, so today my goal is to really talk about two studies that I'm excited about. Data science is kind of a funny area to be working in, especially lately, because generally the data is moving quickly so that funders, when you propose to do something with the data you anticipate being available, they kind of say, well, that's crazy, why would you want to do that, and they don't fund it. On the other hand, by the time you've published something, you're sort of on to the next thing, which is sort of an order of magnitude bigger than what you were doing before, and not that excited to talk about it anymore. So I guess marrying those two, I'm going to be talking about two projects that are neither funded nor published yet. And I've kind of shamelessly or shamefully, I guess shamelessly, co-opted the Warriors logo here, because I think of these projects as falling into this category of trying to build strength in terms of food security by using numbers. It's also a kind of a nod to the fact that I'm going to the Warriors game on Friday. I'm pretty excited about that. And also, I suppose, because it's really a team effort, and I'll kind of point out these guys as we go along, but ranging from postdocs, undergraduates, graduate students, and other faculty on campus. In some ways, unfunded projects are the best, because the people who are involved are really involved for the pure science of it. So I'll talk about two projects, but let me kind of lay the context for those of you not used to thinking about the types of problems we are, which I suspect is a lot of you. So if you think of a typical data science problem, or at least as I think of it, as is often presented, is you've got millions and millions of data points, let's say on web sessions where you're clicking on an ad, or you're rating a movie, or you're buying something. And the data science problem that's given to the statistician or the data scientist is, here's 40 million examples of what happened. Now I want you to be able to predict what's going to happen from things like user info and their past behavior on the web. For those of you who work in genetics, I'm sure you can substitute in the genotypes and phenotypes wherever in that sentence makes sense to you. This would be a typical data science problem that I think a lot of the exciting stuff that has been presented in this series and elsewhere on campus is happening. In food security, the type of data science problem that we sort of envision are things like this. So here are, let's say, 10 million, if we get there, histories of poverty levels and different interventions that happened and how or whether they sort of emerged out of poverty. We want you to predict the intervention that's going to most effectively reduce poverty. Poverty being a key component of food security. Food security, I should have a definition for you. It's basically ability to have enough food to live a basic active life. So on the one hand, you don't want to be too poor. On the other hand, you don't want food to be too expensive. And so poverty and sort of food production or agriculture are really the two of the main pillars of food security. So other examples would be something like this. Here's a million histories of crop performance and various factors that might be influencing crop performance. Predict which intervention will most effectively raise yields or most effectively improve the environmental performance of the system. Or say predict what type of insurance policy you should be providing to this particular farmer and when to trigger their payments most cheaply and most effectively. These are all, I think, the flavor of questions that you see us heading toward over the next 5 or 10 years. But there's a bit of a problem, as you may have already picked up on when I'm drawing comparisons with these other fields, is that we are not there yet on the data side in most situations. Either on the poverty side or the agriculture side, these just historically are not the focus of great measurement. An example is, I like this figure from some colleagues' work, showing you 3 estimates of the maize yield in Malawi for a particular growing season. So this is the main crop in this country. You'd think that there would be pretty good numbers. These are 3 different agencies tasked with sort of coming up with an estimate of the productivity of the crop, so the production per unit land. And you can see that some are as low as 1.5 or so, and some are as above 2.5. So huge variation. This is not the stuff that inspires confidence for going to here are millions of histories, build a model. So I think if I were in the audience, or many of you may be thinking, I came to a data science seminar, and the first thing this guy tells me is, we have no data. What's going on? What the heck, as my kids would say. And I would say that there are really 2 steps to the data science problem as I'm viewing it. One is getting the data in the first place. In other words, taking data that does exist but isn't really what we want and trying to translate that to things that we actually do want, which is really not an issue when you're talking about web clicks or tests that are taken online or genotypes that you're measuring in the lab. Of course, there are measurement errors in all these things, but they're generally measuring the outcomes that you actually are trying to model. Here we have a different problem where we actually have a pretty big step of getting to the data itself. And then we have the second stage, which is, I would say, the fun part, where you're actually trying to draw insight from those. And I think one good thing about lagging is that you can often copy the people who are already with all the data. So a lot of that is innovative or novel when looked at from our own discipline, but in fact, we often are just, let's say, borrowing from other avenues of research, or even just like 538 analytics. I'm a big fan of those. Okay, so how do we generate the relevant data given that we don't have exactly what we measure? And so that'll kind of be the theme, what we want to measure. That'll be the theme of the 2 projects I'll talk about today. And just to give you a sense of the type of data streams we have that might be relevant, I'll talk about a couple of examples. So one is, not going to surprise you, is mobile phone data. And here's a nice example, I think at least, of what some people are doing to try to map population using phone around the world. So people have been doing all sorts of things with phone data. Here's one focused on population. It's a little video, which we'll play. So the density, the darkness of the points are indications of where people are using their phones. And this is France. And you can see that in the weekdays, it's really concentrated in urban areas. And on the weekends, it sort of scatters. And then in the holiday period, which in France is about 4 months long, apparently, they all kind of both go into the countryside and towards the coast. Okay? And then eventually, they get back to work. But it's going to take a while, so let's just hold on. There we go. So now they're back to work. You can see them during the sorry, I know there are Europeans in the audience, and I'm being very flippant here, but they do take long vacations. So this is one obvious kind of application that makes sense and provides actual data on where people are moving. Obviously, in France, we may already have a good sense of where people live, even where they're vacationing. But in other countries, this could be a huge value, just understanding where the people are that potentially would need assistance in times of food scarcity, say. Another application of this is you can not only look at activity from a sense of where are people in a relative sense, but you can look at how much people are, say, topping up their phone cards. And in poor places, this is a very good indication of, potentially a good indication of how flush people are feeling in terms of cash. They'll tend to tighten up in terms of their phone expenditures when they're having trouble meeting their food needs and vice versa. This was a study recently published in Science, which is a nice example of that in Rwanda, where they got access to call records throughout Rwanda and showed that actually if you compare those to household measures of wealth, there's a very good correlation. This is what's shown on the right there. Now, it's often very hard to get access to these phone records, but when you do, they have a lot of information about not only sort of where people are, but how well they're doing. Now, the other, I would say, well, there's several. There's social media. There's all sorts of websites collecting information about people's activities. The one that I'm going to talk about a lot today is satellite imagery. And this is giving you an example of a recent image taken by a local company, Planet Labs, for one of the areas we work on in Uganda. So this is, hopefully you can make it out. The picture isn't showing up that well, but you can see sort of the outlines of individual houses, individual trees. You can see the borders of individual fields here. This is about a 5-meter resolution image taken of Uganda about a month ago. Now, there's been a revolution. I don't know how many maybe are already aware of this, but there's been quite a revolution in the cost of acquiring satellite data. So one way of measuring that is just sort of looking at the number of what we call microsats or CubeSats being launched. Often these are so small, they're the size of shoebox, something between a shoebox and like a dorm fridge size, being so light that they can be launched very cheaply, often just sort of as an addition to an existing payload. And then they can be sort of set up in large constellations, acquiring data, as you see here. And the number of launches has been increasing very rapidly. One way to think of this for those of you in genetics is it's, at least to my mind, it's kind of a corollary of what happened with the cost of sequencing. So the cost of sequencing a human genome, which many of you, I'm sure, are familiar with, used to be about $100,000 for a single individual. And it rapidly fell. Over the period of a decade, it fell from, let's see if my pointer's not working. Let's just say that you can all see that. I don't have a laser, sorry. It rapidly fell by orders and orders of magnitude, from $100,000 to now where it's really at a few dollars. Now with imagery, a few years ago, if you wanted to look at, say, an area that's a smallholder, food insecure agricultural area in a developing country, and you wanted to monitor that with satellite data over time for, say, 1 year, that would cost on the order of $100,000. So it was really prohibitively expensive, certainly for a researcher, but even for any sort of operational organization. Now you can get away, and luckily we've had some partnerships with these companies where we've been getting data very cheaply, but even if you were buying it, you can probably get away with $10,000. And on the horizon is really the potential to get data for almost free, and what you'll be paying for is the analytics that go along with the data. So there's been a real revolution, and just like the genetic sequencing costs going down revolutionized what you can do with genetic data, I hope I'm not going out on a limb there. I think every geneticist I know tells me it has revolutionized what they're doing. It's going to revolutionize what we can do in terms of monitoring the Earth, and in particular in terms of monitoring areas of food insecurity. So here's, to give you a sense of that, here's what we had historically for these smallholder areas. This is like a 30-meter resolution of what I just showed you. 30 meters being the resolution of sort of the public data that we get from terrestrial satellites that go orbit the Earth regularly. You cannot make out much detail unless you're really good at squinting compared to something like this. And then there's also data that goes down to 1 meter resolution where you begin to make out the individual trees, the individual maybe even cows, things like that. Okay, so that we have all this data, but the question is, how do we make sense of it? And we have here, I think, a fundamental challenge, which is really, I think, the crux of what we've been dealing with in our group and with colleagues over the last few years, is sure, you have all this data that you intuitively know should be related to what you want to know. You're looking at agriculture, you're looking at houses of poor people, you're looking at all the infrastructure they have to conduct their daily lives. So there should be some connection, but the original problem was we didn't actually have much data to begin with, and all the data science techniques out there, all the machine learning techniques that I know about, you need a big training data set, right? So how do you get around not having training data? You have this opportunity, but you really have to kickstart it. Obviously, one way to do it would have a massive investment in measurements, very direct measurements, but that is extremely slow and extremely expensive, and I have a habit of trying to think my way around extremely slow and expensive things. So one thing we do is we fake it in the sense that we simulate data that we think represents what a realistic landscape should look like. And then we train on that simulated data, hoping that whatever our model learns, whatever our machine learning, say, model learns from that simulated data will have some relevance to the actual data that we then have. Okay, it's kind of like a perfect model approach for those of you who come out of physics. Maybe you've heard that term. It's something that isn't actually that common in the world of sort of environmental research, but I think is quite useful. So we've developed an approach that's specifically trying to do this for looking at monitoring the productivity of agricultural systems. And again, agriculture being important not only because it determines sort of the availability of food locally or even globally, but because most poor people, and maybe I didn't mention this before, most poor people in the world have a lot of their income depending on the productivity of agriculture. It's kind of having this dual role of providing food and also income for most poor. So we really want to know about agricultural productivity in these rural areas. So what we do is we fake it, as I said, because we don't have the data. So we simulate lots of hypothetical farmers. And the great thing about these farmers is that they'll give us any data we ask for. They're not going to lie or anything. The bad thing is that they're fake, right? They're not real farmers. They're only going to be as good as we can sort of simulate their behavior. But we have decades of research on how crops respond to farmers doing things, or how crops respond to weather changes, how crops respond to different soil conditions. It's not perfect, but it encapsulates a lot of useful information. So what we do is we simulate these, and on the right is just shown some kind of sample simulations of crop growth, kind of amount of leaves over the season, peaks and then comes down. That's one output from the model. But we also have things like yields, which is what we eventually care about, the productivity per unit area. Then the second thing we do is we take these measures from the crop model output, and then we translate that to observables, things that we actually think we could see from satellites. So the simple example that we're using here is if a crop is very big, it's going to look very green from satellite. Or we have other wavelengths that we look at. But essentially, there are, again, decades of research where you know if you're looking at something that has a certain leaf area, for example, it should look like this in terms of the wavelengths that you're measuring being reflected off the surface. All right, then once we have like the observables and then the outcomes that we care about, in this case, say yields, we can build machine learning algorithms of whatever sophistication we want, from very simple to very complicated, to try to actually predict the things that we want to measure from what we are able to measure. And this may be, depending on where you are, it may be 3 images during the growing season. Somewhere else it might be 2, and they might have different timings. But because you have this big database of fake data, you can look at whatever timing you want. You can develop different models for different combinations of observations. These lights, I can't really see whether your faces are puzzled or not, but we'll have plenty of time for questions, or maybe there's a clarifying one there.
Sorry, yes, clarification. So if you're simulating something and you're learning aren't you learning the simulation?
Yeah, you're learning. You're constrained by how good the simulation is, for sure. But what you're able to do then is basically have a database that allows you to take a bunch of observations and say, if these crops are behaving the way I think they are, I can predict whether this field should be one of the crops in my simulation that looked really good or one of the crops that looked really bad. So it is not going to it's not going to do great if your model is terrible. On the other hand, your model could get the right answers for the wrong reasons, and that's OK. In other words, if a crop looks really bad because it's diseased or because a pest ate it, right? That's not in our simulations. I didn't mention that, but it's not in our simulations. But in our simulations, we have farmers who don't put on any fertilizer and sow the seed very, very sparsely. That will look a lot like a poor crop to our model, even though the true crop was poor for a different reason. It's just a way of trying to rapidly go from observations to yields, observations both in terms of what we see coming off the surface, what we know about the weather in the area, and get yields. So the proof is in the pudding, right? It's in terms of how well does this work. So I'll get to that in a second. But once we have these models, we can then apply. And in addition to the rapid progress we've made in imagery, we've made, we meaning not me, but in particular Google in this case, has really made a lot of progress in how quickly we can access and process all of the imagery that's ever been collected and is publicly available. So now I can go to any point in the world and ask Google. I haven't been able to do this sort of verbally, but I'm sure that's coming. Google, tell me every picture that's ever been taken of this square meter of land over the last 20 years. And then I can take that and for each year feed it through, and I can also ask Google, what was the weather in this location over the last 20 years? Then I kind of feed it through the model and get my productivity estimate. Does it work? Well, so this is what it looks like when we do that. These are estimates for the US, starting in the US, because those Landsat, those 30-meter pixels are actually good enough to resolve fields in the US. And in the US, we actually have real farmer data we can compare to. Now, the first question most students of machine learning will ask, well, if you have the data and you have the imagery, why don't you just build a model? But again, we're trying this as a test case for when we don't have the field data. So this shows you a few years of where corn is growing. And we determine where corn is growing, borrowing from the USDA has sort of algorithms that they developed to distinguish corn from soybean from other crops. Where's corn growing? How productive is it? Red being very productive, blue being not very productive, about half the yields of the other. So you can see a lot of heterogeneity over time. This is for a small snippet of Iowa. You can zoom out, though, and do it for entire counties. You can zoom out even more and do it for the entire Corn Belt. It takes a little time, but not nearly as much time as it used to. So this is showing how well it's doing on an average basis, showing you the average estimate from our model for corn and for soybean on the right, versus what the true reported data from the farmers to the USDA were. Okay? And you can see that it's working. It's working not perfectly, but it's working pretty well. There is some bias, but the correlation is quite high. We're explaining about 3/4 of the variance across the Corn Belt of productivity. That's at the county level. If we go down to the field level, we're still explaining about half the variance. And again, maybe I didn't say this already, in data science, your data doesn't have to be great if there's a lot of it, right? You can still get a lot of insights. As long as your errors are not somehow correlated with the signal that you're looking for, you're fine with error, right? You just want some signal in there to be able to learn from. Here's a picture of what the average productivity looks like across the 3 main states of the Corn Belt with a little bit of a zoom here to give you an example. And you can see, hopefully, that one, that there's pretty large variations within the whole Corn Belt, but even within individual counties. A lot of interesting variations that we really didn't understand before, or we didn't even really appreciate before, now we can have access to and start to learn from. If I were to show you a video of this, you would also see that those spatial patterns vary a lot from year to year, and we learn something from that. We can also start to sort of pair this with other data that we have or can put together, like what is the cropping history. We can learn quite a bit about how important rotation effects are, for example. Those are the kind of things we can do. Right now we're working with some students to look at how well can you predict things about the soil properties just by knowing the time series of performance in combination with the weather. One other thing that we're doing, it's just an example of something that I find exciting, and exciting, I guess, this would not qualify as exciting in my household, but for me this is exciting. We can look at the yield progress on each individual parcel of land throughout the US. And we can ask questions like, is that uniform progress? Where is the progress happening? Where is it not happening? And one of the things we see, which is interesting, I think, is that if we look at measures of soil quality, and this is what's shown on the x-axis here, is kind of USDA independent measures of how good are the soil on these pieces of land. And we look at the trend yields, again, averaging across all the fields in those particular types of soils. We look at trend yields over time, starting in 2000, going to 2013. You can see that at the poorer soils, we actually don't see much progress over time, whereas in the better soils, we see this big increase over time. Another way of thinking about that is the effects of soil have really grown over time. That slope has really steepened. So agriculture in the US, at least in the case of corn, is kind of a story of the rich getting richer and the poor, in a sense, being stagnant. And this has implications for how we think about the prospects going forward, because if already somewhere on the order of 30% of our land base is not improving in terms of productivity, that's already, an unprecedented thing in our history, and it doesn't bode well. But on the other hand, another implication here is that even within field, we see this. This is showing you overall, but even if we look at within field, what's the average difference between the best parts of fields and the worst parts of fields? That seems to be growing over time, which is kind of consistent with this renewed interest or increased interest in precision management, trying to manage different parts of the field differently. This is actually showing you within county differences. A similar story. We actually don't see it at all for soybean, which in some ways is comforting because it means it's not an artifact of the imagery at all. It's a real effect, and we understand why corn would be different than soybean. I can maybe explain more later, but it's probably not worth the time. This is just an example of some kind of insight that comes right off the bat when you have this kind of data set, even without much other data except for basic soil maps. Okay, so that leaves me plenty of time to talk about the second approach that we've been doing, and this is really with Stefano's group in computer science, which is that you don't fake it. You don't use a model to generate data. Instead, what you do is you use some sort of proxy measurement that you know is not what you want, but you feel like it is related to what you want. And you can use that, leverage any proxy that has a large sample size, leverage that to try to train your model to some degree, and then just do the last bit of training on the very little bit of data that you have. We call this transfer learning, as opposed to, say, simulation learning. And the idea is, I'll explain in a bit more detail. The idea is one that we've been working on with, so Stefano, for those of you who don't know, he's a computer science professor, Marshall Burke, a professor in earth system science. Matt's a research associate. I didn't have a picture of him, so he's always wearing a Nets hat, though, so I put that there. And then, poor guy, is a Nets fan. And then you have really most of the work being done by an undergraduate, Michael, and a PhD student, Neil, working with Stefano and us. And I was going to say really nice things about these guys, but actually I'm worried about them sort of drifting off to work with other people, so I'm going to say that you should never work with these guys. They're very difficult. Okay, so what are we doing? So the idea, at least as a first step, is to take some high-resolution imagery and try to find features that are indicative of poverty. Okay, so for example, you can look at two different images, and I don't know exactly where these are exactly, but the idea is that looking at roof types, you can understand sort of something potentially about the neighborhood, right? You can do this even in the US. If you look at pictures of people have used sort of Google Street View to try to rank communities in terms of how wealthy they are, and it works decently. So can we do this at scale accurately and with unprecedented spatial resolution? The reason that we kind of think it might work is that there's been a huge advance in pattern recognition over the last 3 or 4 years. And this is really Stefano's sort of a wheelhouse, I guess, is that in particular in terms of deep learning, which is really neural network. When I was in school, these were called neural networks, but apparently that went out of vogue, and now they're just called deep learning, which really does sound much better. There's been a lot of advance in sort of deep learning techniques, and then also large training sets on able to train sort of computer vision algorithms put together. ImageNet is the classic example of that, where there's been lots of progress in computer vision, and lots of people at Stanford have been leading this. I haven't been involved with this at all, except more recently with Stefano. Okay, so the idea with deep learning is that it's going to automatically learn, kind of like our eyes do. The idea with neural networks is they're mimicking the neural system. They're going to automatically learn the features that are predictive of a landscape. We're not going to say, look for roofs. We're going to say, here's a bunch of images. What do you think? And And as I said, we don't have the actual data to know these guys are poor, so we're going to do something else. Okay? We resort instead to using night lights. Night lights, for those of you who don't know, these are just pictures of the Earth taken at night, so you can see bright areas as bright and dark areas as dark. This is showing you a more developed part of the world where you can see those bright lights really clear. But if you go to Africa, for example, you'd see a lot of darkness. I probably should have put up a global map of this. So the idea is we feed in a whole lot of locations. We feed in both the night light intensity, which we think is some measure of overall levels of sort of poverty, or it's an inverse measure of poverty. The more light there would be, maybe the less poverty there is. And we feed in all of the daytime high-resolution imagery that has indicative features of the landscape. Okay? So our data-rich proxy is the night lights, and we're trying to, again, leverage this to gain knowledge that might be useful later on. Okay? So this is just a bit more detail on the actual deep learning approach. It's a fully convolutional neural network, which just means that basically, regardless of the size of the image we give it, it can handle it and put it all into the same framework. It's fast to train in the sense that it's not taking forever as some approaches would. And what does it give us? So this is, I'm going to give you some examples of types of images. So we've sampled really thousands of points, night lights. We're focused on Africa, I should have mentioned. I'm going to give you an example of what some of the images produce in terms of features. So for example, some of the features are picking out roads. Okay? It's not really fair to call these roads because we haven't said these are roads. These are just features that the model thinks are useful in terms of explaining variation in nighttime lights. Okay? And one of them being roads here. So you see, you can see with your eyes probably. Again, I don't really have a great pointer. Let's take this one on the left. You see a road going through it. You can see the filter activating there, which means it's picking up that feature. Similarly, and Stefano wanted me to emphasize that it's actually not ever told that it should be looking for roads even, right? Not only that it isn't called a road, but we haven't even told it to look for linear features. It is just picking that up, which is quite impressive. Urban areas, it picks up quite actively, looking for all that speckle associated with urban areas. Farms, interestingly enough, it finds as a useful feature, and it's quite, is important in the model. So we allow with the neural networks, allow the model to train itself what are features that seem to be useful for predicting night lights. Now the question is, are night lights, or more specifically, the features learned by looking at night lights, are these useful for looking at poverty? So what we then do is we have all of these features. For any given scene, we have, say, 4,000 different features that the neural network picked up when it was trying to predict night lights. And now we ask, are those predictive for several hundred, but not very many, instances of measurements of poverty that have been done with household surveys? Okay, and you have different measures of poverty in household surveys. The two main ones are how much money have you spent in the last month, and do you have a radio, do you have a motorcycle, and all your assets. So those two measures we've been looking at in terms of how will we train. And because we have only a few hundred data points and potentially thousands of predictors, we have some regularized model like ridge regression. And this is kind of a summary of our initial results in one country. This was Uganda, looking at the accuracy of our approach, which is in bold there. Just look at the top row there, 0.71. Does almost as well as all of the values, all of the predictors that we might glean out of the surveys themselves. So the surveys are very long lists about different features of the household. So how many rooms does your house have? What type of roof do you have? All of these things. That does a little bit better, but not that much better than this transfer learning approach. And really interestingly, the transfer learning approach, all of these high resolution images, do a much better job than the night lights themselves. Okay, so that's a bit counterintuitive that we've been using this proxy to train on. The proxy itself wasn't that good, but the model we train on the proxy does a lot better. Not only that, but if we take that learning and we apply it out of country, this was even a bigger surprise. It still works well. So let me just explain what this is showing. This is the square correlation between our predictions of poverty and the measures of poverty in the household survey. And we've done 5 different countries now. For each country, we've tried the model trained on data in that country. And we've also and by training, let me just be clear, I'm talking about this second step of training where we're actually building some sort of ridge regression model to translate the features into poverty space, okay? So we're not redoing all of the feature definitions. Those are done one time only. But we're going to be using the data from the individual countries. And in some countries, maybe you'd expect like roads would be a much better indicator of poverty or lack of tree cover, say, whereas other countries which have much more trees, maybe that's not a good measure. So there's a lot of reasons you'd expect something in Eastern Africa, for example, not to work well in Western Africa. So we do a lot of training in country, testing out of country. We also do a pooled model, which I actually haven't shown here, where we test a pooled model that pools all of the data from all the countries. So what's interesting to me is really that, first of all, that these are as high as they are, right? That we're explaining over half of the variation in village-to-village poverty levels within these countries. That's what these correlations are showing you. So you go around a country, you've done a very expensive, exhaustive survey. The World Bank funds these. You've measured poverty for individual villages, and you can explain half of that variation just by looking at daytime imagery sampled around these locations. Not only that, but we don't actually, because of confidentiality reasons, we don't even know the exact location of the village. We just know within 5 kilometers where the village was. So we do well overall. If you actually compare back to the phone records, so that was in Rwanda, they were getting a square correlation about 0.6. We're doing better in Rwanda with the imagery than you can do actually with the actual phone records, which is quite surprising. And the other surprising thing here is that we do, in most cases, we do as well using a model trained in a different country than in the country itself. So the features we're picking up as being predictive of poverty seem to be pretty robust features. Now, those of you might be thinking, what is this guy talking about? I'm looking at Malawi. Malawi is catching my attention. It's true. It's not a universal success story, although Malawi is interesting in the sense that the cloud cover is so high that we actually don't have very good coverage of imagery. So usually we're able to capture about 100 very high resolution snapshots around the village or in the vicinity of the village. In Malawi, that's actually a much smaller sample we're able to get. That's one possible reason. Another possible reason is it's just a different part of Africa with different characteristics. But the fact that we are doing as well, that we're even outcompeting phone records is quite encouraging and surprising. Why does this work? So I mentioned before, it's quite surprising that like the lights themselves don't actually work that well in Africa because it's dark everywhere. In the sense, you can see this here. So this is the average. Again, I don't have. I keep going to. So this is the average. I'm going to make the cameraman work a little here. The average. The blue line just shows you the average intensity for the places where we have actual measures of household. In this case, household expenditures. Okay. So this is a histogram of household expenditures in Uganda. You can see a lot of people are below the poverty line. This is the poverty line here. And you can see that really they're all dark. They're basically the average night lights is 0. Okay? It only really starts to brighten up once you're well above the poverty line. So that's why night lights is really not useful for looking at explaining expenditure variation, because for half of the population it's just too dark to even register on these sensors. But what the night lights does do is tell you something about what distinguishes between a little bit and a lot brighter areas. And that is correlated with things like potentially with roof type. This is the average amount of metal roofs in the sample, which is sensitive to poverty at levels above the poverty line, but also very sensitive below the poverty line. So in other words, we're learning in this space, it seems, and we're translating it to this space. And this is our explanation, I think, of why, is my explanation of why it works. You can tell I'm not a machine learning person because a machine learning person would just say it works. You know, the computer is doing things. We shouldn't try to explain exactly what it's doing. But intuitively, we like to have some intuition about what's going on, and I think that's the intuition. Now, when you have these algorithms, then you can access imagery for much broader areas than we can actually do field surveys. So, for example, in Uganda, we can then predict it for every square meter of the country or square kilometer, let's say. And we produce maps, for example, that look like in the middle. And you can compare that to existing maps that have been made based on government data. And they match pretty well. The top right there is actually missing data in the government records, so that's kind of an indication of how hard it is to do. It's a bit outdated as well, but qualitatively things are matching up in terms of broad spatial patterns. All right, so I am going to end there and leave time for questions. I would say that if you take anything away from this lecture, you can choose one of these 3 or 4. One is that I think just like in lots of other fields like medicine or education or commerce, data science is helping us become smarter and a lot more personalized about how we intervene in case of poverty or agriculture, which are really the two main spheres that we're working on relative to food security. It will happen, but it's not really, I would say it's over-promising to say it's going to happen very soon, although maybe medicine and education are just better at over-promising. But I would say that we're kind of further behind in terms of the data side, but I still think data science is going to be a huge path forward for progress on these issues. And in some ways, the delta is going to be that much bigger because we haven't even had the basic data sets to begin with. So it takes maybe a bit more clever thinking and a bit more time to get to the data, but the incremental knowledge that we can gain is that much more. That's the silver lining, I guess. And there are two approaches we've been trying to use to get past this fundamental data limitation are using simulations and using transfer learning or proxies as ways to train algorithms that can then be used for future prediction. And I would say, like where I started with the Warriors, I expected this to work pretty well, but it's working extremely well. And I think I'm almost as excited about this as I am about the Warriors game on Friday night. So with that, I'll take questions. Thanks.
Brooke has a microphone for those.
Sorry, still a clarification on the simulation thing.
Yeah.
So you have a simulation, you train a model, and now I give you a test example. Instead of feeding it through the model, if you just fed it through the simulation, wouldn't you get the same answer? Because the output of the two things is similar, or I'm just missing something. Right.
So just to be clear, when you have an observation, say from an image, you have an image of a field, a couple images of a field, and you can say, this field has this kind of reflectance. It looks green, not green, whatever. There are approaches that actually would take that, feed it through a crop model that can ingest sort of greenness, simulate how much the plant is growing, and then give you an output. That's one approach that has been used. It's computationally a very expensive and slow approach, and it is prone to all sorts of, let's say, inaccuracies. So I think empirically it hasn't worked that well. Instead, what we're doing is we're saying, let's go into our data set and see what other fields have looked like that at those particular times when I'm observing it. And what's the distribution of yield outcomes that are associated with those fields that look like what I'm looking at. So we're using simulations to populate this database that we then learn from. It's different than trying to feed our observations into the model itself. And maybe the short answer is that our observations are not inputs into the model. Our observations are one outcome of the model, and the yields are another outcome of the model. And we're trying to connect the two with some sort of algorithm. I think she's right behind you with the mic.
Out of personal curiosity, are you able to tell different types of crops based on the wavelengths that they're giving off?
Yeah, good question. I was just talking with an RA today about this. The short answer is it's very difficult. That even driving by a road, unless you know what you're looking at, right? It's not so obvious. Most crops are green, and they're greener when they're doing better. And you can easily, even if a crop on average is a bit different, you can easily mistake variation in biomass or crop health for a change in crop type. So what we do instead is we really rely on the phenology of the crop. So depending on the time of year, I guess, is the answer to your question. So if you look at enough of the year, generally speaking, the U.S. example is that soybean comes on a little bit later than corn, and it lasts a little bit longer. So you've got to look at the whole. You wouldn't want to look in the mid-season. In Africa, the challenge is that so many systems are mixed systems with all sorts of stuff going on. You've got an understory crop, you've got lots of weeds, and it's a continual challenge. So that's kind of another topic that we are trying to tackle in tandem with, if you know it is a maize field, how productive is it? And that by itself is useful for all sorts of reasons, but it would be even more useful if we could also predict what's growing where.
Thank you.
Yeah. And simulations might be useful there, but our ability to do that with simulations is not perfect. Hey.
So one short question, maybe the other one slightly longer. I didn't exactly understand whether there was a dearth of imagery data, and if there was, I was kind of surprised that the same government that puts you as a top priority would have images from here to Wazoo that they could blur and hand off to you, I would think. So the imagery is not an issue.
No, so the imagery is going forward not going to be an issue. Going backward, it's not an issue if you're working in areas that don't require very high resolution. If you do require high resolution, it's not just a matter of what the cost was. It's also a matter of them not being acquired. So if you're interested in parts of the Soviet Union, you can get really good high-resolution imagery going back. But in Uganda and Kenya and India and all these places, it's harder.
And then the second question is about interventions. I'm curious about intervention and also maybe if it's related to the maize and the soybean. That's still a mystery to me.
Okay. Interventions will really depend on where you are. So if you start like at one end of the spectrum in the US, so one interventions we often have is with our policy. Like we will incentivize or not incentivize things like rotating crops, right? So that's one thing that can be important both in terms of how well performing the crop itself is and how risky that enterprise is in terms of drought, say, effects, but also in terms of what the environmental externalities are for growing that crop. So other sort of on-farm interventions that farmers want to know about is which parts of my field are going to respond differently to inputs, which parts of my field need more or less fertilizer. At the other end of the spectrum, in terms of the agronomics in Africa, because so one of the main interventions is providing credit and insurance to farmers, and providers of those are so wary of doing that because they just don't understand what their basis is, their risk is. So this could help in terms of just understanding the riskiness, but also understanding what interventions beyond providing credit and insurance, like technically what interventions work. And there's lots of experiments going on where people go out and they subsidize for like a random subset of the farmers, just like they do in medicine. It's a randomized trials now. They'll bring in new seeds or a particular type of fertilizer, and there's disagreement about which type of fertilizers will work best, so they'll have different ones. The problem is that those are really underpowered in terms of their ability to actually pick up effects. And partly is because they just can't afford to do that many of them because they have to go back to the houses and monitor. So what we're trying to do with this stuff more directly is try to increase the power of these randomized trials to learn quickly about what interventions are working. So that's an example there. But there's all sorts of theories about what's limiting productivity in Africa. And I think the real key is getting a process going that can quickly learn about what works and what doesn't.
Just to follow up from your point, I'm right here.
There you go.
In terms of agriculture and poverty intervention, specifically on the African continent, how do you see accessibility in terms of this data to entrepreneurs on the continent? And then how do they make use of this data to increase productivity levels? And also from a business perspective, how do they kind of get people out of the poverty trap?
Yeah, it's a bit similar to my previous answer, I guess. My personal view is that at that end of the spectrum, expecting farmers themselves to make a lot of use of this data is unrealistic, although there are some efforts in that direction. But I don't think that for a really smallholder farmer, they're not that constrained by sort of information on how their crops are performing. More so, they're constrained on just knowing what would work and having confidence that it's worth the investment, and also having the insurance to back them up if their investment goes wrong, which is what most farmers of the world have. So in India and Africa, I think the biggest sort of beneficiaries of this type of technology will be the farmers, but it'll be indirectly because of the ability of providers of credit and insurance to learn more quickly about, what are the right things to recommend, and what are the, returns on investment, what are the risks associated with it, and moving out of this, I think, historical situation where just nobody knows anything, basically, and they're prescribing things that work somewhere totally different.
On On the lights and the question of why do they work so well, I'm wondering about the fact that the lights are telling you more. You're getting additional information from the lights than just that there's enough money for electricity. With all those IDs, all the identifications you showed us. So how much is, based on what you've done so far, how much is explainable by the fact that there's more? You're getting, from going to the lights to what is actually on the ground, you're getting more information. And if it's not at all, if you're not using that at all, then, or if that doesn't explain it, could you do even better by getting more out of the fact that you can know it's a road, or you can know that there's, that shape means something?
I'm not, we should probably talk after, because I'm not sure I understand the question exactly. But one thing we do see is that, and I showed this a little bit, but the lights themselves don't work as well as what we capture in the high-res imagery. The lights plus, if you add the lights into what we get with the high-res imagery, it actually doesn't help that much either. So I think it's true that, as I was saying, the lights are reflective of general processes of development that matter, but they're only reflective after you reach a certain threshold. But the things that also continue to increase after that threshold, they are also effective below that threshold, in other words. So whether it's roads, whether it's the existence of certain types of roofs or large buildings, or very well-organized farmland, or we don't know. And that's sort of, we're never going to know exactly what it's picking up. The best we can do is test out of sample as much as possible to make sure we're not overtraining to something that is specific to that area. But I think that one of the things to realize is that nightlights has been used a lot in the last decade in economics because of this intuitive association between development and electricity and lights. And I think we see that there's something to that, but it's not nearly the tight relationship that you can get from some of the things that you can see in the daytime, if you have the resolution. All right. I'm sorry. As I said, the lights are a bit much.
So do you see this simulation learning and maybe even the transfer learning as something as short term until you get enough data? And if so, how short term? Is it something like 5 years, or in the order of 50 years from now will you have enough data to not require this?
Yeah, that's a great question. I should mention that students who are interested in these kind of topics should come talk to me. Whether it's for my group, there's lots of private sector interest in this area now. I don't know if you're a student, because I can't really see you, but that was like a question that students have asked me. I would say that I don't know. I think that it depends on what outcome you're talking about. I think that there are, as I was saying, with the mobile phone, for example, if you can get access to enough of those records, and maybe that will happen, it's harder to get access to those than to imagery, that you may end up being able to train directly on the data that you have. And that's I think, very plausible. But again, that's only another indirect measure. So what you really want is direct measurements of the well-being or the expenditures. And so maybe as digital payment systems become more common, you would have something more direct about that. I think on the agricultural side, having worked in this area for a long time, having seen how bad, even if you go in with field data, how hard it is to get a good measure of productivity in the field, I think we'll have to basically combine the simulated data and the real data and maybe weight them differently over time. But I think that for a long time, the simulations will help will help relative to just using the raw data. And I don't see that changing in the next 5 or 10 years unless, one possible exception I think is people have gotten pretty good with phones at actually, if you take a picture at the right angle in a field, you have a pretty good measure of the leaf biomass at that particular point in time. And if there's a big sort of crowdsourcing campaign to go and do that for tons of fields over the year, and then maybe if they can also develop with that image processing, picking out the grains themselves and digitizing that, that's a possibility. But otherwise, I think the simulations work pretty well. And again, I think is a question of what do you need? So R squareds of 0.5 to me are quite exciting from a scientific standpoint because you can get all sorts of insight into cause, effect, and the importance of different factors. They may not be that exciting to somebody who's trying to operationalize an insurance program and needs to know, did this farmer meet this target or not? So maybe for different applications, you would push in different directions.
David, if I may add, Data Science at Stanford is a forum and a birds of feather session. We have a group of faculty advisors. If you go to datascience.stanford.edu, you'll see who they are, and it represents quite a diversity. Our leader is Professor Ewan Ashley, who sends his regrets. One of the things that happens when you are a cardiovascular doctor is you sometimes end up saving patients' lives, which is exactly what he's.
He tells me that. So he's my neighbor, and he tells me that. Oh, I gotta go on call. I think he's actually upset because I've been. He has this elite athlete trial that I've been offering for like 3 years to volunteer, and we have this disagreement about if I should be in the control group or the elite athlete group.
Yep. We take great pleasure in the diversity of applications and field, of data science, which is why it's such an honor to have you here. Our first talk was on Google Search with the Vice President of Google Search. And the next one was on the new statistical methods by Trevor Hasty to accommodate tall and wide data as we now are seeing. Our following talk was on pharmacological farm GKB stuff from Russ Altman to find patterns in abstracts of published articles. And our next talk is on February 17th, perhaps, by a lady called Caitlin Smallwood, who is the Vice President of Data Science for Netflix and has been for other companies. And Netflix is one of the most powerful exponents of data science. It will be in actually Li Ka-shing as a departure from here. Li Ka-shing 120, of course, it's all on the website. We hope to see you there. And again, thank you so much. It was a pleasure to listen to this.
Thank you.